kickoff. And the title is Quantum Scaling in Many-Body Quantum Systems. Ceren, please.
Okay, thank you. Also, thanks for inviting me to this interesting workshop. Happy to be here. So my name is Ceren, and I'm a new assistant professor at IU Bloomington and a research scholar at Harvard. And today I'll tell you about quantum scaling in many-body systems, which is basically a research program that I had started back when I was a postdoc. Okay, so come on, work. All right, good. So, all right, so I just started my group, as I said, and we study quantum many-body physics in and out of equilibrium. That includes a couple of different directions. Maybe I'll stay here. No, you might not see, I'll stay here, okay. And these directions include quantum simulation with Rydberg atom arrays. We do the quantum simulation on one of the commercial machines. And then, but I also do from background, really a theory for cold atoms in optical lattices or Rydberg atom arrays. Also a little bit of superconducting qubits. And we study light index phenomena in quantum matter, which includes Floquet engineering, but more recently, cavity QED, quantum electrodynamics engineering of quantum materials. That basically trying to understand whether we can change the quantum phases of matter with light or coupling to enhance vacuum fluctuations. But of course, the main topic of this workshop, I like to think about the concepts of quantum chaos, ergodicity, thermalization, and how we break it. Okay, so that's what I will be talking about, particularly the scarring phenomena. But before that, okay. Yeah, I have to be here. I'm sorry. It's not enough range. Okay. So, but before that, I'd like to give you a quick highlight of this a recent work, which might also interest you. So in this recent work, we basically did a quantum simulation by using this Rydberg atom array, commercially available by Cura Computing. So what we did is like very quickly, what we did is like we operated this machine away from its usual operational limit. So basically where we're working is the lattice distance is actually at the blockade radius, which then we found that this particular limit, first of all, is the limit that you have to work if you want to realize a transverse field Ising model on this platform. But importantly, if you're on this limit, you're also like susceptible to atom motion more than any other limits. So what that makes actually like atom motion has like an effect in quantum many-body dynamics that we measured basically, and leading to this like slower, anomalously slower dynamics than what we expect. Normally we expect quasi-particles to move ballistically, but we found that experimentally and then theoretically like we modeled it, the sub-ballistic behavior basically in the spread of correlations, which also led to like, for example, if we look at the Fisher information density, we would see a logarithmic increase, all of which suggests like slowing down instead of thermalization. So following that, we were able to write down some minimal spin model, which basically captures this atom motion as a random disorder in the couplings, in the spin-spin interactions, and also the longitudinal field, which we wrote down with the normal distribution that depends on like the hardware parameters, like the C6 coefficient, Rydberg interaction coefficients, lattice, distance, as well as this positional uncertainty, which is the most important thing to capture that atom motion. So I'll be very happy to chat about this offline because this is not what I'm going to talk about right now. Okay. All right, so going back to the main topic of quantum scarring, to set the stage, I'd just like to mention very quickly about thermalization, which you heard all about. So in the field of quantum thermalization, perhaps the one fundamental question that we are interested in, as you know, if there is no heat bath, if there is no decoherence, of my interacting many-body system, can I still like see thermalization, or will the state that I prepare remain indefinitely as it is? So the answer to this quick answer is no. Closed interacting quantum systems thermalize, and in fact, they do exhibit an ergodic behavior, which we understand in terms of random matrix theory. So this is fundamentally pretty interesting, but also could be practically important in the era of quantum technologies, could be important, for example, for quantum information processing and storage. Okay. Well, one pathway to thermalization you just heard is the eigenstate thermalization hypothesis. In a nutshell, ETH is basically that one eigenstate alone that we took in the microcanonical energy window can describe the long time equilibrium properties of the Hamiltonian. And for an interacting closed many-body system, we basically see the microcanonical ensemble to basically predict the behaviors, okay? So that means, for example, we call these states basically thermal eigenstates, which is going to come out a lot in this talk. And what does this mean? For example, we define a microcanonical ensemble, and from there we can define the temperature for this, ETH satisfying system, large many-body system. That also practically means something. If we actually bring like a smaller system to this big system, like a qubit, it will actually thermalize to the with the right coupling between the small system and the big ETH satisfying system. It will actually thermalize. Qubit will thermalize to the temperature that we define, the effective temperature that we define based on this ETH. Hence, we can, for example, drive, master equation coming from the ETH ansatz. Okay, I'm not going to talk about any of this, but I find this very interesting because this actually answers whether temperature emerges in a closed system, and that's a useful temperature too because of this thermodynamic property. And also answers in a way like how does a quantum bath become a bath in the first place and can thermalize smaller systems. Okay, so as I said, thermalization is the main thing that we study, and it's also accompanied with a mechanism for ergodicity, which we understand in terms of the random matrix theory. So this is a pretty large topic, but very quickly, basically what we understand from ergodicity, how we define quantum ergodicity or quantum chaos, as you will see in the literature. We look at how the energy levels are distributed, okay? So, and then there are a couple of different objects that we can look for this, but the one common thing that we look at how the nearest neighbor energy gaps are distributed. And if they're not overlapping, if there's no energy states coming on top of each other, that means energy repulsion. We would see these basically with the distribution of Gaussian distributions, okay? So this is basically what we call universal fluctuation laws that we see in the energy levels. So what does level statistics gets us is actually the short-range energy correlations. So it will tell us what is the probability of finding one energy level given that there is an energy level at some other energy. And recently, actually, people have been focusing on what's called spectrum form factor, which can also capture longer range energy correlations. One signature that we actually see in the spectrum form factor is this ramp plateau behavior. Okay, this is in time basically. Spectrum form factor is written in time, and the ramp actually tells us that there is a spectral rigidity in the system. It is a signature of random matrix theory emerging in our realistic system and level statistics particularly. Okay. So these are what we so far know about thermalization and ergodicity, and these concepts have been studied for decades at this point. And also the other thing that's studied is how we break this ergodicity, this understanding of quantum ergodicity. And there are a couple of different pathways to do this. Now, one that is known is integrability. So your model might be integrable, meaning it might have extensive number of conserved quantities. We know that that's not stable to perturbations. So realistic systems in particular, tend to be non-integrable. It's actually harder to do them integrable. Anyway, it was first realized in a quantum gas experiment. the 2006. And then the second one is what people call many-body localization. This is like the many-body, it was envisioned to be, many-body, the generalization of Anderson localization. However, as we know, like it is now, we know that it is in the thermodynamic limit, it is not basically stable to the perturbations. So it doesn't seem to be, sorry? So yeah, we basically know as like prethermal many-body localization at this point. What I'm saying is that, from the times that we can actually like realize in the lab, there seems to be many-body localization, but we don't know whether many-body localization is actually there in the thermodynamic limit, right? So this is under debate, active debate at this point. So that's actually like the true statement to say. So you can see here in the block experiment, in fact, that you can see the imbalance starting from a quench, from an anti-ferromagnetic state, does show like, the effects of ergodicity breaking. However, we don't know whether this is going to be the case in infinite time. So hence, now in the community, people also say prethermal MBL, just to be open to that, possibility. All right, that brings me, I'm not going to talk about MBL, right? Good that I'm not going to talk about MBL. So I'm going to talk about quantum scattering. Maybe it's also actually a hard topic to talk in terms of this. But anyway, so what is quantum scattering? It also goes under Hilbert space fragmentation. And it was first found in an experiment, in actually one of the first Rydberg atom array experiments. The Rydberg atom arrays are, non-integrable systems. So we don't expect some oscillations to occur after doing a quench. However, this is what they saw. Some anomalous oscillations. They were robust, basically, to increasing the system size here, as we see from the data. Later, it was found that actually the origin of these oscillations are coming from these like non-thermal, non-chaotic many-body states that are embedded in an otherwise, chaotic sea of many-body states. So you can see here these like black ones here. Okay, so the area of quantum many-body scars is pretty active, and there are many different quantum many-body scars that are found, maybe every day, I'm not sure. But anyway, so there are certain, I think, some criteria that one can say, okay, I found a quantum many-body scar. So, and those are like, you show that they are low entropy, non-chaotic, non-thermal states, but also importantly, their numbers are negligible, like in the thermodynamic limits. So their numbers increase polynomially, for example, in an exponentially increasing Hilbert space. So I find that as a very key way to define quantum many-body scattering. Anyway, so depending on the model, for example, the model that describes the Rydberg atom array, they might be actually placed in an equal energy spacing, which then, can actually give rise to this very nice oscillations. Okay, but what is quantum scar in the first place? We say quantum many-body scarring, so it must be some many-body generalization of quantum scars. At least that's one thing initially. But quantum scars actually goes back to Rick Heller's paper from 1984. Quantum scar is a quantum eigenstate with an enhanced probability density around the periodic orbit. Okay, so what this means is actually, first of all, we're talking about a model that has a phase space, has some sort of semi-classical limit where we can talk about a phase space. And, the scarring orbit has to be unstable. That means when we calculate the Lyapunov exponent, it is non-zero. And physically, what that means, if I'm on the, this orbit with a small perturbation, I can actually leak into the chaotic phase space around me. So it's important that unstable periodic orbits are actually living in this chaotic phase space. And then that gives us some revival of the state fidelity in time. Okay, then we can ask the question, is there really a connection between quantum scarring and quantum many-body scarring? Like, where are those periodic orbits? And I'm going to say, to date, there is no evidence for the relation between a phenomenon of quantum many-body scarring and quantum scarring. Why? Because in the works that I know, at least, there is no relation, there is no association of quantum many-body scars and the periodic orbits that are like unstable and embedded in chaotic phase space. Unstable periodic embedded in a chaotic phase space. So then that basically keeps this open. All right, so this basically this question, what motivated us to start this research program? First, we wanted to start from some multi-atom physical system where there is a well-defined semi-classical limit. Hence, we can go and study phase space and hopefully find some unstable periodic orbits, which then we can go ahead and like check whether they're scarring the quantum states and the quantum eigenstates. And we can understand the spectral properties of these quantum eigenstates, whether they are showing the same properties with quantum many-body scars, for example. From here, this was actually a quantum gas, okay, with an all-to-all interactions, collective interactions. So even though the system itself a many-body system, the model that we worked with was can be mapped to a few particle systems, so which motivated us to make our model formally many-body, which then gave rise to these quantum scars in a many-body system. And it turned out to be a spin-1 chain. And then very recently, we showed the ubiquity of this phenomena that can actually arise in a generic spin-1/2 system. Hopefully, I'll have time to come here as well. Meanwhile, there was an experiment done on the first theory that we proposed, which I'm going to describe in a second, like the platform and the theory. And also, we had the time to introduce this notion of anti-scarring. I'm not going to spend time on this, but very quickly, it means that if there is scarring of some states, some other states must compensate for it, okay? Meanwhile, very important to note, Hummel, Richter, and Schlage, had the similar ideas for Bose-Hubbard model. And they were working mainly with like the high filling fractions of the Bose-Hubbard model, and in showing that quantum scarring in the way like of unstable periodic orbits in chaotic phase spaces is possible there too. Okay, so starting with the this first part, multi-atom quantum system, what we work with is a spinor condensate, a spin-1 spinor condensate. And we work under what's called single mode approximation, which basically simplifies the system a lot. What that does is like we basically assume the spatial part of different spin components are the same, such that the entire wave function can separate the spin and the spatial part separately. And the spatial part is then just gets into normalization, and we just basically end up with a spin Hamiltonian, the spin Hamiltonian that you see here. Okay. It's an interacting spin Hamiltonian. There are density interactions, and this is what we call spin mixing interactions. These 0, 1, etc. Those are the spin index. So basically, what this is like a multi-mode, the all-to-all interacting quantum gas. Okay, that's also what actually makes this model, makes the system in the model sense, in the model level, a quadratically. Having a Hilbert space that quadratically increases in the system size. Okay, so it's kind of like a formally equivalent to actually a few particle system. Okay, and this system is actually known very well in the spinor condensate literature. And you can ask, okay, how does this approximation, whether it's valid, etc. So the single mode approximation is actually a valid approximation when you have like a homogeneous trap, and also when you have low number of atoms. And in fact, there are a couple of different experimental groups that are studying spinor condensates in this particular SMA single mode approximation limit. That's also why it was just realized the model that we...
Sorry, a very silly question just to be sure that I don't get lost from the very beginning. These A and A dagger are bosonic operators, right? Okay.
They are. Mm-hmm.
So essentially you have three, let's say, harmonic oscillators.
Yes.
Okay.
Yes. And those are basically for atoms, right? So bosonic operators for atoms. Okay, so but this Hamiltonian is nice, has phase transitions, etc. But it's integrable. Okay, so we have to break integrability. That's what we propose. We say like if you add like 2 in-plane rotating field to this, and do a unitary transformation, and under certain conditions, quite experimental, we can end up having this simpler Hamiltonian, okay? Let's just go here. This green part is the interaction part. Red part is mode mixing part. You can see A0, A plus here, mode mixing. And that's the part that breaks integrability in this very simple model. It's a nice model because, again, there's a semi-classical limit. I'm going to show in a second. We write down the semi-classical limit, which is a mean field limit that is, valid in large atom number limit. And it has, we write this down in terms of the coherent state basis. Anyway, so even with a small p, small integrability breaking, we see a diverging density of states in the middle of a spectrum, which helps with, having chaos, quantum chaos. So now let me very quickly present you what we found in this work. So as I said, the model is nice because it has a semi-classical limit. So we can go ahead and write down study the phase space, okay? So the phase space we found is a mixed phase space. It is, you can see here is the color is the Lyapunov exponent. So we see a family of U-poles embedded in the chaotic phase space, one U-pole in each energy, basically. And then there is a region where there are stable periodic orbits living in this phase space. We find this basically by writing down our spinor atom in the coherent state basis, as you can see here, which gives rise to a four-dimensional phase space. So, okay. And we were, okay, so this is basically a Poincare section at a particular energy density. We can go ahead and look at the quantum eigenstate at that particular energy density. So this is what we're doing here. So what you see here is that quantum eigenstate that we found exactly at that energy and its projection, okay? So it's kind of visualizing the state, quantum eigenstate through the Husimi distribution. Husimi distribution is the overlap of my quantum eigenstate and the coherent state basis here, which then shows us this enhancement around the unstable periodic orbits. So this is what a quantum scar is, okay? So that quantum eigenstate is actually a quantum scar because it is scarred by the unstable periodic orbit. So this gives rise to in quantum dynamics. If you start your dynamics with an initial state, with a coherent state on the U-pole, then basically we see this robust first fidelity enhancement. Robust in the sense that it doesn't go away, the amplitude stays the same with the increasing atom number. So this wouldn't happen if you actually did start from a coherent state of U-pole, and that's because you can see that the fidelity decreases with this the system size here. Okay.
Sorry, can I ask here at this point? So
yeah.
how do you define thermodynamic limit here?
Thermodynamic limit is basically n goes to infinity. The atom number goes to infinity. Yeah.
Okay.
Yes. Probably you can have Wigner-Dyson distribution, yeah, for any of these. That basically just, I think, choosing this function, changing the Husimi with the Wigner. Sorry, Wigner, maybe I missed a Wigner representation. I was.
No, I think.
Yes. Yeah, let me come there. Yeah. Actually, yes. So we chose that state. I'm sorry. We chose that state actually from, okay, so this is the spectral properties, particularly the entanglement entropy that we calculate for this model. And that state actually comes from this part, which we call ergodic band of states. And they're actually saturating the maximum entropy that you can have in the system. And if you look at the properties of these states here, they show Wigner-Dyson statistics. So this is actually an interesting point that I wanted to emphasize. So let me mention that when we look at this spectral properties of the quantum model, we find these two sets of states, okay? Most of the states are these chaotic states that are showing the Wigner-Dyson, also showing ETH properties for the local observables that can be measured in lab. Spin zero atom population is what's typically measured in the lab. And you can see that this smooth function property of the diagonal elements of the eigenstate expectation value. So But then there's this other states here that you see. These are regular towers. Actually, these are towers, and we can exactly write these states. Okay, I'm sorry. We can write approximately through the spectrum generating algebra. However, there are still towers of states, and they're kind of regular states. First, when we were studying this, these actually looked like to us like, okay, are these quantum many-body scars? However, when you look at first of all, okay, you look at their properties. These states show Poisson distribution if you just take these like regular states. And they actually like show a Hissumi distribution, which are associated with the stable region of the mixed phase space. So they do look like quantum many-body scars, but they are not quantum many-body scars. We call them regular states mainly because their numbers are actually quadratically increasing in a quadratically like increasing Hilbert space. Okay, so they're basically proportional to how the Hilbert space increases. So this is why, like, okay, these are regular states. They're really associated with stable periodic orbits. Anyway, so in the end, like, they also show very good, like, long-lived oscillations in the local observables and very big, like, fidelity revivals. But in the end, what this work showed us, okay, so the spectral properties of scars, quantum scars that we found looked pretty different from those of quantum many-body scars in the literature. And in contrast to that, we found certain spectral properties that look more like quantum many-body scars, but they are actually regular states. So that kind of made us, okay, well, can we actually have these things coming up in a formally many-body system? Right, so far, this is an all-to-all interacting quantum gas. So that's what we did. We took this model and put it in a lattice, okay? So with the unit filling, what this turns out to be is a spin-1 chain, okay? We follow from actually from the same Hamiltonian that we wrote the gas. It's just went to the other element. Instead of all-to-all, now it's there like nearest neighbor interacting. And we again have like, these actually come from normally in the quantum gas from the Zeeman fields. But anyway, we kept them. So this gives rise to like a z-square term on site. And then there is like a driven transverse field. So by following exactly what we did for the gas, we do a unitary transformation and then like average over one full Fourier period to get an effective Hamiltonian. And this turns out to be like a Hamiltonian with a transverse field and some sort of like some sort of a spin model where there is a ZZ interaction and then some flip-flop interaction. These flip-flop interactions, we wrote it in terms of kappa operators. Okay, so what kappa describes is really just the transition between the different levels on site, okay? From 0 to 1 and -1. These kappa operators are connected to the usual spin-1x. Okay, so now, like, we study like a particularly like large integrability breaking limit, p is equal to 0.5. In this particular limit, like, we found this, the volume law entangled, as well as, volume law entangled, as well as, thermal states. And at this point, what I need to mention is that now this is a formally quantum many-body system, and many-body systems don't typically have a semi-classical limit. There is still a mean field limit here, but it is not the semi-classical limit. So with this in mind, we defined a mean field manifold, okay, basically that holds our mean field ansatz, which we assume to be translationally invariant. So that means each spin is in a coherent state, but the same coherent state, okay? So now this defines like a classical manifold in my big Hilbert space. And I can ask the question, like, how much of this classical manifold, classical equations of motion that I write here is affecting my quantum many-body dynamics, okay? So one nice thing is that now we have this phase space that we studied from before, and we can go ahead and check the projections of these states that we took in the middle of a spectrum. And we saw that these many-body states do have like enhancement around the unstable periodic orbits at different energies. Okay. And then we can see, actually, we can look at the quantum many-body dynamics, whether that scarring that we see is actually affecting the quantum many-body dynamics. And if we start the dynamics at a coherent state on UPO, we see these like oscillations in the populations, okay, and spin zero populations. And those the oscillations happen at a period, which is the UPO period, okay? So you can see from here, it's the same UPO period. If we do this with a state from an off UPO, we don't see this property here. And we can understand this actually from the eigenstate occupation numbers, which is the overlap of the initial state with the eigenstates here. We find these towers of states here that are, separated from each other with the UPO frequency. So this immediately tells us basically, yes, we need to see some sort of effect in the dynamics. But of course, okay, not of course, I will explain why I say of course, but it eventually thermalizes like these observables that we are looking at, okay? And then if we look at this, the Eigenstein occupation numbers for, some chaotic state of UPO, we don't see that kind of property. We also define some spectral density that can actually tell us this kind of properties, okay? All right, so what is the take-home message? Quantum dynamics do follow, to certain time, not long times, definitely, sometimes, follow on stable periodic orbits hidden in this classical chaotic phase space. We call them thermal quantum anyway, guys, because eventually they thermalize, and it's going to be clear in a second why they have to thermalize. But we also changed the, this P, the transverse field strength, which controls the integrability breaking. And we found that behavior changes dramatically. Actually, when we go to small p, the oscillations are long-lived. And we were curious, okay, what is the origin of that? Is that still, that could be related to unstable periodic orbits? So if you go to that small piece, first of all, the spectrum changes dramatically. Most of the states are chaotic, but then we start having these regular looking states, right? So, and they have also like either subvolume law or area law entanglement. Importantly, their numbers are lower than the Hilbert space dimension. In fact, that's basically the criteria of quantum many-body scars, okay? It follows all of that. But in the end, if you look at the projection, we find them, they're associated with the stable part of the phase space. So they are regular states, basically. And I do like to call them regular states. Anyway, nowadays calling regular states, at the time we called them non-thermal QMBS, quantum many-body scars, because we weren't really sure. Yeah. Anyway, so that brings me to this unifying picture. We've been talking about the Lyapunov exponent, how Lyapunov exponent changing the, affecting the many-body dynamics. But for a many-body system, there's actually another stability, another stability quantity that we should look at always, and that's the leakage. That's because, we're writing down a classical manifold, like this red thing here, right? And a quantum state, like there will be always a rate of this quantum state leaving this manifold into the rest of the Hilbert space. That's what we call as leakage. It's the physical intuition behind, and it was defined actually by this paper and then was calculated many times in the literature. It is formally the difference between the exact time derivative and for us the mean field time derivative. If you do time-dependent variational principle here to get the classical equations of motion, this becomes TdVP time derivative. So what we need to look at here is when we look at the leakage average over like the period, the periodic orbit period, what we expect is, for example, for the quantum many-body scars in the literature, you expect this to be like a very low value. And that's exactly what we see actually for small p's. So that's also consistent with these regular states that we found. That's like, a quantum many-body scar candidates, basically. But for the large p's, actually, we find relatively large leakage, which actually explains why, this when we start the dynamics, with this large P and on UPO, eventually the oscillations have to die and the system needs to thermalize. That is also consistent with seeing the volume law and the ETA satisfying eigenstates. Here, very quickly, let me show how the leakage on the phase space looks like. So we find that, for example, for small p, the periodic orbits are mostly in the northern hemisphere, which is also a low leakage region, which explains like, why these are like long-lived oscillations. These give the long-lived oscillations. It's also a stable region, basically. If you look at like the p is equal to 0.5, where we found like the UPO scarring, we see that those unstable periodic orbits like traverse around a lot, and importantly, they spent most of their time in this high leakage region. So that just means that the quantum many-body state becomes entangled pretty quickly and leaves the mean field manifold. Okay. Okay, does the Hamiltonian need to be fine-tuned? It looked like, like the Kappa operators, etc., looked pretty fine-tuned, right? So very recently, we showed that that doesn't have to be the case. If we start actually, we can write down a very generic spin Hamiltonian, let's say spin 1/2, with some like nearest neighbor interactions and the various fields that we can have here. In this particular case, we actually assume a different mean field limit. Okay, so S goes to infinity instead of system size goes to infinity. In this case, basically what happens to the classical picture is that we have these classical rotors that are precessing and in the effective magnetic field in the mean field limit, basically. So when you look at this, actually, you see that generically such states, will be giving rise to a chaotic phase space with, chaotic trajectories. However, there are some UPOs living in this generic chaotic phase space. One of them is this like translation invariant, the states, where each of the atoms or each of the sites actually spins showing the same direction. The other one we call is interaction suppressing, which means when you like focus on one of them, the overall interaction is 0 around you. So it becomes this very simple classical equation of motion. So these are, we calculate the Lyapunov exponent for these, and we found that, yeah, there are indeed unstable periodic orbits embedded in this generically chaotic phase space, very high dimensional. And then we can ask, do these UPOs scar eigenstates? So for these, again, we need to, we need to do some projection on the mean field ansatz that we chose. So we have these two different mean field ansatz. And we look at basically again, like a semi-distribution of our eigenstates on these states, on these, the manifold of states. So that corresponds to more physically a sphere, okay, with these angles being relevant for us. So we actually project specifically on that theta eta, the plane. And while they're loading, let me tell you what they're for. So we looked at multiple different spin 1/2 Hamiltonians, but this particular one that I'm showing is a mixed field Ising model. The properties are here. So here, like we're showing like some states that many states that we chose from the middle of the spectrum, and you can see that these states do show some some sort of structure according to the unstable periodic orbits that live here. For the TI, translation invariant, and IS, interaction suppressing. These states were chosen from the, again, as I said, middle of the spectrum where there's a volume law, and then there is like an ETH satisfying states. Okay. So maybe an important point here before finishing up, that I am coming to the end of my time, I see it. So these states, like when we look at their like time average projection, actually we find that if you start an initial state on UPO, it's more likely to be founded on UPO compared to off. So in a way, like, even in long time and high leakage out of the mean field manifold, time evolving quantum many-body state remembers its birthplace, where like it was initiated on the scarring UPO. So let me make this very clear. It's like a relative effect, okay? So you need to compare like the probability here and here, like on and off UPO. And that's exactly what shows here. In the system size, increasing, we see these like 4 as coming out as the relative effect. So it's more likely to be found on UPO than off UPO. However, if you look at the absolute values, it's as expected from like, this volume law, etc., it's exponentially decreasing. All right, so that brings me to the end. So I think we're like, coming to a particular point where we can classify quantum scarring based on the classical and quantum instability or stability together. The first one, is the case where we have a chaotic classical dynamics, right, with a non-zero Lyapunov exponent, and then the leakage is being zero in the thermodynamic limit. So basically it becomes exact in the semi-classical limit. There is a semi-classical limit, which was the spinor condensate that I talked about. And the second possibility is there is integrable classical dynamics, no Lyapunov exponent, stable basically, but then also low leakage, so low quantum leakage. This is to my knowledge, pretty much most of the QMBS literature is in, I think. This is what we find, at least in our work here as well. And the third case is like chaotic classical dynamics, but relatively large quantum leakage too. This was what we called here thermal quantum many-body scars. There were a few cycles of oscillations which was following the UPO. And then there comes this very interesting case where, can we have a case where a UPO confined within a low leakage region of a chaotic phase space? So you have a non-zero Lyapunov exponent, but also, the low leakage. So this would be this would lead to strong quantum scarring of many-body eigenstates due to instability in the associated phase space, due to unstable periodic orbits, basically. This will also mean that quantum many-body dynamics that we initiate at these special states will be approximated well by this unstable classical dynamics, and can give us a better understanding of the Hilbert space. However, it's actually not that clear to me whether this can be possible. To my knowledge, there is no example of this. And I'm not sure that it's possible because, just imagine that we're basically talking about, we were talking about whether we can have a regular and stable region of a many-body Hilbert space that can be described by a chaotic and unstable classical phase space. So that kind of if this is not possible, probably this could give us some sort of no-go theorem about the impossibility of strong quantum scarring of many-body states by unstable periodic orbits. Anyway, so because of I'm running out of time, I'll just say that we're also thinking about other things like the practicality of these fundamental concepts, etc. And by this, I'd like to thank my brilliant collaborators and you for your attention.
Thanks a lot. Questions? Let's go with the closest.
When you talk about these quantum stable regions, can you have any kind of dynamics that will just happen and then somehow you fall into this stable region and stays there, or
you mean forever it stays there?
Yeah, or for a long time.
It's leakage is pretty low. That leakage tells you the rate of leaving the manifold. I mean, if you're building entanglement, eventually you're going to leave the manifold, but that's just going to happen in a very long time that probably cannot be detected by experiment. That's why it makes very interesting this, regular states or quantum many-body scars in literature. What makes them very interesting and perhaps practically important too. Yeah. They can stay there a long time, basically. Yeah.
Sorry if my question is too basic, but I'm not very.
Such thing. It's just
Okay. 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 I'm not very. What I know about quantum mechanics is one thing. One thing that I know about quantum mechanics is that the probability of going to A to B is the same as going to B from B to A. So in the same way that you talked about leaking from this manifold into the chaotic space, wouldn't you also leak back some amount?
Okay, so you're saying the going A to B, B to A, like there's basically time reversal symmetry in the Hamiltonian, in fact, in our unitary dynamics. Um, well, of course, there will be a probability of like, going back there, but like, it's most likely it will go to the rest of the Hilbert space, I would imagine, assuming there could be, if there is some sort of ergodic theorem like applied. That's what I would say.
Okay, thank you.
More questions? Okay, over
Interesting
there.
question, by the way.
So just to clarify, where is the Rydberg atom experiment on the list of your 4 possibilities, and what should we call that observation?
Thank you very much for this very interesting question. So I think the Rydberg PXP model, the quantum many-body scars, so far my understanding is also from your paper is, with this 3 bond-dimensional phase spaces that you guys had written, they're like you were associating with the stable periodic orbits. So I think I would say like irregular states for them. I don't know what you think. What do you think? What is your idea on this?
Well, I mean, it's a sort of, it's not easy to answer, but I mean, I would still call it a scar. I don't know, but I'm biased here, so.
Yeah. Well, I mean, I am also not like 100% sure. I am not 100% sure of anything. But anyway, so for this also not, because I totally see the perspective, okay, if I went to higher bond dimension state, if I write down an ansatz with a higher bond dimension, what is the guarantee that it's not going to be turned out to relate to unstable periodic orbits? I totally see that perspective too. It's from that perspective, yes, I agree with you. But from what we have as evidence so far, it does look like a regular behavior to me. Yep, that's it. Yep.
Maybe then the follow-up question. So in your case of lattice model with P1/2, as far as I remember, so you show that your evidence shows that like you have unstable periodic orbits, right? And
Yes,
this
we do see
quantum
unstable.
many-body scars, which you call quantum many-body scars. But in the very beginning, as far as I remember, you mentioned that one of the property of quantum many-body scar should be low entanglement. And we don't see in this rainbow picture any low entanglement. Can you comment on this?
So that's the thing. That's I try to create that differences in 2 concepts. So I am what I call quantum many-body scar as like a connection to some unstable periodic orbit. Not really, the definition is not based on, in this kind of definition, it's not based on like, whether you have a low entanglement or not. So quantum many-body scars that like most of the people know today, if they don't know the classical, connection to the quantum scarring, like sorry, the single particle quantum chaos community, then yeah, like definition there is exactly what you said. So we need to basically at this point we need to clarify, I think, the definitions a little bit. Yeah, that's why I call them either non-thermal quantum many-body scars, the one that you're referring to, or regular states. At least the ones that we are studying, they're definitely regular, we can say, because there's some association with a stable region in the phase space that we wrote down. If there is like any other evidence that I see, there is a connection to unstable periodic orbit, and at the same time, like, we're seeing the relatively low leakage, then that will be my case 4, and I think it's very interesting. But I don't see that yet. I don't see any example. To my knowledge, there is no. Please tell me if there's. Yeah.
Do we have more questions? Okay, if not, we can thank Ceren again.
Thank you.